Welcome dear learners. We are studying quantum chemistry and in this module we are discussing molecular term symbols. The contents of this module are term symbols, atomic term symbol, symmetry notation of molecular orbitals, molecular orbital configuration of diatomic molecules, molecular term symbol determination, selection rule for transition and allowed as well as forbidden transitions. First of all, term symbols. In quantum mechanics, the term symbol is an abbreviated description of the angular momentum quantum numbers in a multi-electron atom. Angular momentum arises from two kinds of motion, the spin motion and the orbital motion. Thus, the angular momentum quantum numbers include spin angular momentum quantum number and orbital angular momentum quantum number. So, term symbol is an abbreviated description of these two quantum numbers, spin angular momentum quantum number and orbital angular momentum quantum number. It is related with energy level of a given electron configuration. It can be considered as a shorthand representation of energy associated with a particular electronic arrangement. So, term symbol is the shorthand representation of energy state associated with a given electronic configuration. Now, atomic term symbol. In atoms, electrons are present in atomic orbitals. So, we can represent electronic configuration of atoms. Based on a particular electronic configuration, we can derive a term symbol. So, the atomic term symbol is given by this expression. That is, atomic term symbol is 2s plus 1 Lj, where each terms S is the total spin quantum number, or simply S is called total spin angular momentum quantum number, and the quantity 2s plus 1 is known as the spin multiplicity. Next one L, that is known as total orbital quantum number or total orbital angular momentum quantum number. And finally J is called total angular momentum quantum number. It consists of spin as well as orbital angular momentum components. So, these are the notations used in this equation, in this expression. So, by using this expression, we can compute atomic term symbol. Now, in computing the term symbol, the spin orbit coupling interaction is assumed. That means, there is a coupling between spin angular momentum and orbital angular momentum. That is denoted as LS coupling. This LS coupling is again known as Russell-Sanders coupling. In an atom, there may be the possibility for different terms or term symbols. However, there is one and only ground term symbol. The ground state term symbol can be predicted or determined by using a set of rules called Hund's rules. Now, the ground state term symbol based on Hund's rule is very easy to figure out the ground state term symbol from so many term symbols if it is in front of you. Once the terms are known, they can be arranged in order of energy and we can pick out the ground term based on the Hund's rule. What are the statements of the Hund's rules? The first one, the terms are placed in order depending on their multiplicities and their S values. The most stable state has largest S value and stability decreases as S decreases. This implies that for a given set of terms, pick out the term with the highest multiplicity. The term with the highest multiplicity is least in energy and hence it is the most stable term or ground term. So, ground term is associated with the highest multiplicity. Now, for a given value of S, the state with the highest L value is more stable. Suppose we are having three terms. All terms have a same multiplicity. then which one will be the ground state? In such a situation, we have to pick up the term with the highest L value, then take it as the ground term, since in a given multiplicity, the term with the highest L value is most stable. Finally, there is one more statement for Hund's rule to determine the ground term symbol. This is applicable if there is still any ambiguity. That is, we cannot find out the ground term based on first and second set of rule, then only the third rule will be valid. If there is still ambiguity, for given values of S and L, the smallest j value is the most stable if subshell is less than half filled, and the biggest j value is most stable if the subshell is more than half filled. That is, as a final rule, we have to fix the value of j. If the electronic arrangement or if the given configuration is less than half filled, take lowest j value, that is L minus S. Modulus of L minus S is the lowest j value. And if the configuration is greater than half filled, we have to take the highest j value, that is j is equal to L plus S modulus, that is the highest possible j value. So, by using these three rules, it is easy to find out the ground state term symbol if there are so many term symbols available. Now, we can exemplify the determination of ground state term symbol by taking Cr2 plus ion as an example. Now, we are going to determine the ground state term symbol for a Cr2 plus ion. First of all, we have to represent its electronic arrangement. We know that chromium having atomic number Z is equal to 24, and it is having electronic arrangement, outer electronic arrangement 3d5 4s1. This is having exceptional configuration. So, this is the configuration of the chromium atom, and chromium 2 plus is having a configuration that is 3d4 4s0. 4s0 you need not represent. So, the electronic arrangement is 3d4, and 3d4 arrangement can be represented like this. There are 5 d orbitals, and the ml values are -2, -1, 0, +1 and +2. These are the ml values, and I have 4 electrons here in Cr2 plus, so I have to put the 4 electrons based on Hund's rules. Pairing of electron takes place only after all the available orbitals are singly occupied. And first of all, I have to compute the term L. L is equal to modulus of sigma ml, modulus of sigma ml. So, electrons are now present in -2, -1, 0 and +1 term. -1 +1 will vanish. So, -2 plus 0 is equal to -2. Taking modulus, I will get L value is equal to 2. If L value is equal to 0, 1, 2, 3, etc., the terms are like this. This is S term, this is P term, this is D term, and this is F term. So, L is equal to 2 implies the term of the present ion, that is Cr2 plus, is L is equal to 2, that is D term. L is equal to 2 implies D term. So, I got the value of L as 2, and hence the term is D. Now, moving on to the computation of S. S is equal to sigma ms, modulus of sigma ms. We have to add the spin quantum number values of the unpaired electrons present in the system. So, here we can see the presence of 4 unpaired electrons, and S value is equal to 2. That is, all electrons have the same spin. So, if all have a clockwise spin, then the total S value is equal to 2. If all have anti-clockwise spin, then the total spin is equal to -2. In any case, we have to take the modulus. So, the value of S is equal to 2, and hence the spin multiplicity is equal to 2s plus 1. 2s plus 1 is equal to 2 into 2 plus 1, that is equal to 5. So, I got the values of 2s plus 1 as 5, L is equal to 2 or D term, and finally, I require to have one more quantum number, that is J, total angular momentum quantum number. J can have 2 limiting values. J may be L minus S as the minimum value, J may be L plus S as the highest value, and the different values of J ranges from L plus S minus 1, L plus S minus 2, all are modulus, etc. up to L minus S modulus. So, minimum value is L minus S and highest value is L plus S. As per the Hund's rule, we have to take up lower J value. This is because Cr2 plus is D4 arrangement, the half-filled configuration is D5 and D4 arrangement is less than half-filled. So, we have to take a minimum value of J and J should be equal to L minus S, and hence the result is L is equal to 2 and S value is also 2. So, 2 minus 2, that is equal to 0. So, J value is equal to 0. Therefore, the ground state term symbol for Cr2 plus is 2S plus 1 Lj equal to 5 term D and J value 0. This is the ground state term symbol for a Cr2 plus ion. This we determined purely on the basis of rules of term symbol as well as the Hund's rules. This about atomic term symbol. Now we have to discuss molecular term symbols. You know the fact that atoms combine together to produce molecules. In molecules, electrons are present in molecular orbitals. Prior to determine the term symbol, we have to represent electronic configuration first. So, in the case of atoms, we have to represent electronic configuration of atoms. So, to determine the ground state term symbol of molecules, we have to represent electronic configuration of molecules. In molecules, there are molecular orbitals. So, we have to familiarize the molecular orbital configuration, and we are going to discuss the molecular orbital configuration. Prior to that, we have to study or understand the symmetry notation of molecular orbitals. We are familiar with so many molecular orbitals like sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, so and so. And we need a new notation based on symmetry. That notation is called symmetry notation of molecular orbitals. So, prior to study the determination of the molecular term symbol, we have to stick on the symmetry notation of molecular orbitals. Molecular orbitals based on two symmetry operations can be represented. That means we can use two symmetry operations to represent a molecular orbital based on symmetry notation. That means we have to take a particular molecular orbital and we have to perform two symmetry operations. Based on the result of the symmetry operation, we have to give a symmetry notation. What are such symmetry operations? The two symmetry operations are there. The first operation is the rotation about the molecular axis. We have to take the molecular orbital and to perform rotation about the molecular axis. If such rotation leaves the molecular orbital unchanged, it has no nodes along the axis, and then the molecular orbital has a sigma symmetry. When the molecular orbital has a sigma symmetry, if the rotation about the molecular axis keep the molecular orbital unchanged, then there will be no nodes along the axis and that molecular orbital belongs to sigma symmetry. If this operation changes the molecular orbital, then there will be nodal plane along the molecular axis. In such a case, the molecular orbital has sigma symmetry. So, when we can put sigma symmetry and pi symmetry, we have to take a molecular orbital first, perform rotation about the molecular axis, observe the result. If the rotation changes MO, then it has pi symmetry. If there is no change in MO, the molecular orbital has sigma symmetry. That is, sigma symmetry is assigning if and only if the molecular axis rotation leaves the MO unchanged. Now, the second symmetry operation. The second symmetry operation is the inversion through the center of molecule. That means we have to take a molecular orbital and perform center of inversion. If center of inversion leaves the molecular orbital unchanged, then the molecular orbital belongs to G symmetry. G stands for Gerard parity. If there is no center of inversion, then the molecular orbital belongs to U symmetry. U stands for Ungerade or ungeride parity. That means we can give G or U notation to the molecular orbital based on the second operation. So, on a sum, we have to perform two symmetry operation. First one being the rotation about the molecular axis, where we get two type of molecular orbital with the sigma symmetry and molecular orbital with the pi symmetry. Here we are performing the second operation, that is inversion, and this inversion classifies molecular orbitals again into two symmetry, that is G symmetry and U symmetry. So, based on these two operations, we can classify, we can arrange different molecular orbitals based on their symmetry. And after the performance of two symmetry operations on molecular orbitals of diatomic molecules, we will get some final result. And the result of such symmetry operations are shown here. It can be observed that all sigma orbitals have sigma symmetry. That means, if you are taking a sigma orbital, for instance it is sigma 1s, and perform molecular axis rotation, there is no change. So, sigma orbitals have sigma symmetry. Similarly, all pi orbitals have pi symmetry. That means, if I am taking a pi orbital or a pi star orbital and perform molecular axis rotation, then the arrangement changes. That means, all pi orbitals have pi symmetry. Moreover, this result is also very important regarding to center of inversion. All sigma orbitals have geride symmetry. All sigma star orbitals have ungeride symmetry. All pi orbitals are ungeride, whereas all pi star orbitals are geride. So, these are the result of symmetry operation, two symmetry operation that we performed on each and every molecular orbital. So, based on the symmetry operations, two symmetry operations, rotation about the molecular axis and the center of inversion, we got these results, and we have to represent the molecular orbitals based on this consolidation. Thus, based on the above results, the first 10 molecular orbitals, they are shown here in the common notation. The first 10 molecular orbitals can be assigned symmetry notation, and this is the tabular illustration of the symmetry notation of first 10 molecular orbitals. We have the 10 molecular orbitals, first common 10 molecular orbitals like sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px equal to pi 2py, pi star 2px equal to pi star 2py, and finally sigma star 2pz. Each orbital transformed into symmetry notation like this. This is sigma 1s. Sigma 1s transferred into 1 sigma g. The reason is all sigma orbitals have sigma symmetry and sigma orbitals are geride. So, I put sigma g. Since this is the first sigma orbital appears in front of you, I have to put 1 as a notation. So, 1 sigma g. This is 1 sigma g. 1 is a prefix here. So, 1 sigma g. Similarly, I am taking sigma star 1s. Sigma star 1s. So, sigma orbitals have sigma symmetry, and we know that sigma star orbitals are ungeride and sigma star orbitals are geride. So, I am carry over this star here also. This is the first sigma star or antibonding orbital that appears in front of you. So, I put 1 sigma star u. Similarly, sigma 2s belongs to 2 sigma g. Sigma star 2s belongs to 2 sigma star u. This 2 indicates that this is the second sigma orbital that appears in front of you. 1 is already used here, so I have to use 2 here. In a similar sense, we can represent all other orbitals like this. Sigma 2pz orbital transformed into 3 sigma g. Since the sigma orbitals are geride, so g is also here. Sigma is carried over here. This is the third sigma g orbital in front of you. 1 and 2 already used, so this is 3 sigma g. Moving on to the pi orbitals, you know the fact that pi orbitals are ungeride, so u is here, u subscript is here, and this is the pi orbitals have pi symmetry, so pi is carried over here. Also, this is the first pi orbital that appear in front of you. So I put 1 pi u. That is having degeneracy. So 1 pi u equal to 1 pi u. This is because pi 2 px and pi 2 py orbitals have same energy. Similarly, pi star orbitals are gyroid. So 1 pi star g. This 1 indicates that this is the first pi star orbital appears in front of you. So 1 pi star g equal to 1 pi star g. And finally, sigma star 2p is transformed into 3 sigma star u. Therefore, this about the symmetry notation of first 10 molecular orbitals. They are 1 sigma g, 1 sigma star u, 2 sigma g, 2 sigma star u, 3 sigma g, 1 by u equal to 1 by u, 1 pi star g equal to 1 pi star g, and the final one 3 sigma star u. You have to keep the order. This is the regular energy increasing order that is appeared in the case of common molecules, and we have to give MO configurations also based on this. Now, we can put MO configuration based on the new symmetry operation. H2 plus is having only 1 electron. So this configuration is 1 sigma G1, that is the MO configuration. For hydrogen there are 2 electrons, therefore the configuration is 1 sigma G2. And for H2 plus, for helium He2 there are 4 electrons, and He2 plus there is only 3 electrons. So the configuration is 1 sigma G2, 1 sigma star U1. That is the configuration. For lithium, atomic number 3. So Li2 has a 6 electron. Thus the configuration is like this: 1 sigma G2, 1 sigma star U2, 2 sigma G2, 2 sigma G2. That about the configuration. Now we are going to take boron, carbon, nitrogen, oxygen, fluorine, other elements, and we have to think on very significant result that in the case of second row elements up to nitrogen, energy of the sigma 2p orbital is slightly higher than that of pi 2px and pi 2py. So we have to keep such a thing in mind whenever we have to represent the electronic configuration of these elements. So we are entering into configuration of boron. Boron is an element with atomic number 5. So B2 having 10 electron. So the arrangement begins like this: 1 sigma G2, 1 sigma star U2, 2 sigma G2, 2 sigma star, 2 sigma star U2. Now the regular order is 3 sigma G2. Unfortunately, boron being second row element and there is exceptional configuration. So 1 pi u appears in front of you. So 1 pi u1 equal to 1 pi u1 is the configuration. 2, 2 plus 2, 4, 6, 8, 9, 10. So here there are 10 electrons. This is the configuration of boron. This is somewhat different from regular configuration because after 2 sigma star u, the orbital coming is not 3 sigma, but instead of that 1 pi u appears in front of you. This is because energy of the sigma 2p orbital is slightly higher than that of pi 2px and pi 2py. Moving on to carbon. Carbon is having total 12 electrons, and this arrangement is 1 sigma G2, 1 sigma star U2, 2 sigma G2, 2 sigma star U2, then 1 pi U2 equal to 1 pi U2. 2, 4, 6, 8, 10, 12. So 12 electrons are here. Here there is also exception. And moving on to nitrogen, there are 14 electrons. The configuration is similar up to here, and then 1 pi star G1 equal to 1 pi star G1. So this 12 plus 2, that is equal to 14. For nitrogen, there are 7 plus 7 equal to 14 electrons, and this is about the configuration of the nitrogen. But for oxygen and fluorine, there is no exception, and we have to give the correct configuration like this. For oxygen, there are 16 electrons, and the notation is like this: 1 sigma G2, 1 sigma star U2, 2 sigma G2, 2 sigma star U2, then the next orbital is 3 sigma G. So we have to put 3 sigma G2, 3 sigma G2. Actually for nitrogen there is an exception. Instead of 3 sigma G, there occur 1 pi u first. 3 sigma G will appear later. That is the exceptional configuration of second row elements up to nitrogen. So for oxygen there are 16 electrons. then 2, 4, 6, 8, 10, then 1 pi u2 equal to 1 pi u2, 14 are there. Then next one, 1 pi star g1 equal to 1 pi star g1. So 2, 4, 6, 8, 10, 12, 14, 15, 16. So in oxygen molecule there are 16 electrons. And finally we are discussing the case of fluorine. We have to add 2 more electrons to this oxygen to get to fluorine, because in fluorine there are 18 electrons, 9 plus 9, 18 electrons. So for fluorine the last configuration is 1 pi star G2 equal to 1 pi star G2. This about the configuration, all others are same. This about MO configuration of diatomic molecules, and molecular orbitals are shown in symmetry notation. Now we are discussing molecular term symbols. Molecular term symbol is given by the notation 2s plus 1 lambda, geride or ungeride, positive or negative. The term positive or negative will be appeared if and only if lambda is equal to 0, that is only if there occurs a sigma term. S is the total spin angular momentum quantum number, lambda is the quantum number which represents the total orbital angular momentum, G or U represents the parity, plus or minus superscript is applied only to sigma state, that is when lambda is equal to 0. This is about the molecular term symbol. We can move on to each term. First term is total angular moment, total spin angular momentum quantum number. S is computed by this relation sigma msi modulus. That means we have to pick out all the unpaired electrons and add their spin quantum number to get the value of S. And as in the case of the atomic term symbol, 2s plus 1 will give the multiplicity also. Then moving on to the computing of lambda. Lambda is very important, which can be computed by this modulus of MLI. MLI represents the component of angular momentum along z direction for ith electron. This is getting by a simple way. For the electron under consideration is a sigma. That means for a sigma electron means an electron present in the sigma orbital. For a sigma electron, the value of MLI is equal to 0. However, if your electron is present in a pi orbital, then for pi electron, MLI is equal to plus or minus 1. Suppose there is only one pi electron, then you have to put MLI is equal to plus 1. If there is one more pi electron, we have to put minus 1. Plus 1, minus 1, plus 1, minus 1, like that. For the first pi electron, it is plus 1. For next, it is minus 1, so and so. So, sigma MLI is equal to 0. For sigma electron, MLI is equal to 0. For pi electron, MLI is equal to plus or minus 1. On adding, collecting together the MLI values and taking modulus, we will get the value of lambda. Lambda is called symbol or term symbol or term. If lambda is equal to 0, the term is called the sigma term. If lambda is equal to 1, the term is called the pi term. If it is 2, it is called the delta term. If it is 3, it is called the phi term. So, these are the four possible terms, nothing but sigma, pi, delta and phi term. Now, assigning parity. Parity is assigned. If the electronic configuration is G1, then parity is G. That is, one electron is present in a geride orbital, G1 is marked as G. And if one electron is in G and other electron is in U, then the parity will be U. If one electron is present in an ungeride case, then U1 is also U. But if two electrons are present in ungeride parity, that is U1 into U1, that is equal to U2, that can be taken as G. This is about the assigning of the parity. And finally, we have to give plus or minus sign. The plus or minus sign is applicable if and only if you are having triplet arrangement, half-filled pi orbitals. For triplet arrangement, for half-filled pi orbital, we have to give negative sign. In all other case, we have to give positive sign, and this sign is applicable if and only if lambda is equal to 0, that is when sigma term appears in front of you. That is, we have to assign negative sign only if for triplet arrangement, in the half-filled pi orbitals. Now, energy ordering can be done with the help of the Hund's rule. The term with the highest spin multiplicity is lowest in energy, and for term with the same multiplicity, pick out the value with the highest lambda having lowest energy. So, we can now determine the molecular test symbol for hydrogen as a representative example. First, we have to write the configuration. The configuration of H2 molecule is 1 sigma G2, this about, and the 2 electrons are like this, they are in opposite direction. So, the value of S is equal to 0. So, multiplicity, no unpaired electrons are here, so S is equal to 0. So, multiplicity 2s plus 1 is equal to 1. And we have to compute the value of, lambda. Lambda is equal to modulus of sigma mli. Here you can see the presence of 2 electrons, and 2 electrons are sigma electron. I already mentioned that for a sigma electron value of mli is equal to 0. So, lambda is equal to 0. Lambda is equal to 0 means the term is sigma, and since this is not a triplet arrangement and half-filled pi orbital, we have to assign a positive charge, and this arrangement is G2. G2 is G1 into G1, so the parity is derived. Based on by clubbing all these parameters together, we are getting the final result as the term is sigma, multiplicity is 1, parity is derived, and the sign is positive. This about the molecular term symbol of hydrogen. Now we are taking another example. Determine the molecular term symbol for oxygen molecule. We already learned the electronic arrangement of oxygen molecule, which consists of 16 electrons at the time of representing MO configuration. This is the MO configuration of oxygen molecule. This shows the 16 electron arrangement, and now we have to take the outer shell arrangement, that is 1 pi star G1 equal to 1 pi star G1, and it should be noted that these 2 electrons have the same spin. Therefore, the value of S is equal to half plus half, and multiplicity equal to 2s plus 1 equal to 2s plus 1 equal to 2 into s plus 1, that is equal to 3. So, this arrangement represents triplet oxygen. So, this arrangement is the triplet arrangement. Now, we have to compute the lambda value. Lambda is equal to sigma mli modulus. I already mentioned that for sigma electron mli is equal to 0. For pi electron mli is equal to plus or minus 1. For the first electron mli is equal to plus 1, and for the next electron mli is equal to minus 1. Therefore, sigma mli is equal to plus 1 plus minus 1, that is equal to 0. Therefore, lambda is equal to 0. Lambda is equal to 0 implies the sigma term is the sigma term. Now, we have to assign other parameters, sign as well as the parity. It should be noted that this is G1 into G1. G1 into G1 is also G. Therefore, the term symbol has a parity G, and multiplicity is equal to 3. And finally, we have to assign the sign. In assigning the sign, for half-filled pi orbitals in triplet state, we have to give a negative sign. Therefore, this 3 sigma G minus is the molecular term symbol for oxygen molecule. And while assigning the priority sign, we have to keep the fact that for sigma term, we have to give a negative sign if and only if it is in half-filled pi orbital triplet arrangement. This is the situation. Now, we are discussing selection rules for electronic transition. Selection rules are restrictions that govern the possible or allowed transition from one state to another state. The selection rules have been deducted experimentally and corroborated theoretically. These are the selection rules in governing transition between the terms delta lambda is equal to 0 plus or minus 1, delta S equal to 0, that is there must be no change in multiplicity. These transitions indicate that there must be no change in sign, plus to plus is allowed, minus to minus is also allowed, but plus to minus is not allowed, and there must be a change in parity. Based on this selection rule, we can pick out allowed and forbidden transitions. Now in this question, there are two transitions shown, and you have to pick up the allowed and forbidden transition based on the selection rule shown there. First part is lambda is equal to 0 plus or minus 1. We know lambda is equal to 0, 1, 2, 3, and this is sigma term, this is pi term, this is delta term, and this is the phi term, sigma pi delta phi. So this is sigma pi transition. Sigma pi transition means delta lambda is equal to 1 minus 0, delta lambda is equal to 1, that is allowed. So delta lambda is allowed. First rule is allowed. Second case, 3 to 3. Multiplicity 2s plus 1, multiplicity also 2s plus 1. If S is same, multiplicity will also be same. Since LHS and RHS have same multiplicity, delta is equal to 0, so that case is allowed. So sigma pi allowed, multiplicity allowed, then there is a change in parity, G to U, that is also allowed. Here there is positive sign only on left side. In right side there is no need for representing the sign. If sign is applicable on both the sides, then only we have to look onto the sign. Or sign is applicable only to sigma sigma transition. So we have to ignore the third selection rule. So all other three selection rules, so first, second and fourth one is valid here, and this transition is an allowed transition. Now we can move on to the last transition. This is from 3 to 1. There is a change in multiplicity. So there is a change in value of S. So the second rule is not obeyed, and hence the entire transition is failure, even though other points are okay. If one selection rule is not valid, the entire transition will be blocked. So no doubt the second transition will be not an allowed transition, or it is a forbidden transition. Thus in this module we have studied molecular term symbols, its determination, and allowed and forbidden transitions. That's all about this module. Thank you.